Hey there, it's Miss B, and in this video we're looking at the Unit 4, Lesson 11 practice problems, or cumulative practice problems, for Illustrative Math Algebra 1. So, let's get started. This is more about domain and range. So, for our first question here, we have a child tosses a baseball up into the air. On its way down, it gets caught in a tree for several seconds before falling back down to the ground. Select the best description of the range of this function. So range, I know that range, this is my output values. So I want to look at all of my output values. So it's falling from a tree. I have a couple different things here. We have a couple options. So this says the range includes all numbers from 5 to 12.5. Well, that would be 5 to 12.5 up here. That's the child tossing the baseball. But we do also, using our graph, have numbers that fall below 5, so that doesn't actually work. Because, if you notice, it falls down to the ground, and the ground is 0. So, not going to quite work. We do have a maximum on our graph here, though, of 12.5, it looks like, so we'll say 12.5. So the range includes all integers between 0 and 12.5. Not true. This baseball is not just going to just skip to whole numbers. It's actually going to fall the entire way instead of just teleporting from 12 feet to 11 feet to 10 feet. So it's not going to be just integers. I mean, it does include those, but it's not just those. Our third option here for C, it says the range includes all numbers from 0 to 8.5. 8.5 looks like maybe where it's in the tree and it gets stuck. But it goes above that, so not that one. Let's look at our last one. It includes all numbers from 0 to 12.5. I would agree with that. It's going to go from the ground all the way being tossed into the top of the tree. So it is going to include all of these numbers from 12.5 down to 0. So D is correct, and D is going to be our answer. Question 2, or problem 2, either way, we're looking at a field trip. So to raise funds for a trip, members of a high school math club are holding a game night in the gym. They're selling tickets at $5 per person. So $5 per person. And the gym holds a maximum of 250 people. And the amount of money raised is a function of the number of tickets sold. So tickets sold would be input, because we have that output is a function of input. So I know money raised is my output, and that's a function of tickets sold. So the domain is all of my input values. So if they're asking me about domain, it's input. So what statement accurately describes the domain? All numbers less than 250. So 250, it is going to be less than 250 because it holds a maximum of 250 people. But because we are counting people, it is going to be whole numbers only. So we can't just say all numbers. It's only going to be whole numbers. And whole numbers are the same as integers. That's what part B says here. It says all integers. But I can't have more than 250. And I also can't have negative numbers. I can't have negative people attend. It's possible that I have 0. All positive integers, again, we still can't have over 250. So D is again going to be our answer because it's all positive integers. So positive whole numbers that are less than or equal to 250, or we can say like up to 250. Problem 3. We have C gives the cost in dollars of a cafeteria meal plan as a function of the number of meals purchased, N. So let's label some inputs and outputs here. Cost in dollars. If it's giving that, that's the output. And it as a function of the number of meals purchased, N, that is input. So now the function is represented by the equation C of n equals 4 plus 3n. We want to find a value of n such that C of n equals 31 is true. This is a fancy way of saying, hey, please find out what number you can plug in to make it equal 31. So we're going to say 31 equals 4 plus 3n and solve for n. So let's subtract 4 from both sides. So this would be 30, 29, 28, 27. This would be 27 is equal to 3n. And then we would divide both sides by 3. That would give n by itself. And we would end up with n is equal to 9, because 27 divided by 3 is 9. So the number of meals is 9. So there is a part B to this. So let's switch to the back of the page. It says, what does that tell you about the cafeteria meal plan? Well, that tells us that the number of meals purchased, if that was 9, would cost $31. So we would say, if you purchase 9 meals, the plan will cost $31. Or 9 meals costs $31. I'm a little longer-winded sometimes. Okay. Question 4. Lynn completes a 5K, so running a 5K. Using a combination of walking and running, here are 4 graphs that represent 4 possible situations. Each one shows the distance in meters as a function of time in minutes. So luckily for us, they have all of these labeled, so they have distance in meters and time in minutes on all of the axes here. We're going to just match these with their descriptions. All right, so I would say first, one that stands out to me is this straight line. So that's graph 1, and let's match that up with something here. So for graph 1, if I have a straight line, that is a constant pace. So that looks like this one for C. Lynn jogs at a steady pace for the entire race. So C looks like it goes with graph 1. So I'll put a C next to it there. Lynn jogs at a steady pace the entire race. I'm also just going to put a C up here on the graph. So I'll put my letters in both places. Okay, graph 2. It looks like kind of jogging, then maybe running, going at a faster rate. So casual pace, going at a faster rate, maybe stopping for a second and then continuing. Because if there is no progress made, meaning the output value or the distance in meters is the same for a certain amount of time, that means the person stopped. So let's look at our different situations here. Starts out running, slows down to a jog. After 10 minutes, she stops for a water break, and then she runs the rest of the way. That maybe seems like it could work. Oh, actually, this says that Lynn starts out running and then slows down, but this one here we said was kind of slow and then speeds up. So we have the opposite thing going on here. I think this looks more like graph 4, where we have this and then a speed slowing down, meaning it's not going as vertical. So it's slowing down a bit. Then there's a period where they stop and then running the rest of the way. So I'm going to say that graph 4 is going to be A. And this will be A. Okay, so then this other long situation here, option D, this is probably going to be the one we were looking at for graph 2. Lynn starts out walking, then moves to a steady run. After 15 minutes, she stops to stretch a cramped leg and then walks the rest of the way. That seems like this starts out walking, then speeds up and runs, and then is like, oh no, I have a cramp, and then starts walking again the rest of the way, slowing down. That sounds more like this option here. So D is going to be graph number 2. So like here. So let's check that B actually makes sense for graph number 3, because it's our only pair left. We want to make sure we didn't make any mistakes. Lynn starts the race walking and gradually getting faster and faster. So that means our slope, or our graph here, should gradually get more and more vertical. Because the closer you get to pointing straight upwards, that means the faster you're changing over time. So, yep, I agree. This should be B. So this is B. And that is our question number 4. So if we move on to problem number 5, that's on the next page for me. The graph H shows the height in meters of a rocket t seconds after it was launched. Find H of 0. What does this represent? So that's our first job. H of 0, that is the output when the input is 0. So that's going to be right here on my graph. That looks like it is 15. So we're going to say H of 0 equals 15. And then we're going to say what it represents. That represents the height we launched the rocket from. Is the height that the rocket is launched from. Okay. So B says describe the domain of this function. So that is all of our inputs, because domain means input. Oops. Input. So describe the domain of this function. Well, we're not going to use negative time, but we can go from 0 because we do have a starting height. And then it looks like, oh, excuse me, it looks like it goes to maybe, how far over does this go? Right here looks like 4.6 or maybe 4.75. We can estimate, but we're going to estimate what that amount is. So we can say the domain, and because this is time in seconds, I am allowed to have every single little tiny point in between each of these. We can definitely have fractions. So the domain is all numbers from 0 to 4 points. Maybe we'll call that 4.7. And our estimate doesn't have to be exact, so we can say to approximately 4.7, or we can put the little wiggly line in front of it to mean like about or around that. Now we want to describe the range for part C. So we want to find what our tallest value is here. To me, that looks like 35. And we know our rocket is not just going to be teleporting distances. It's going to be launching and then coming back down, but it's actually only going to meet that height of 35. So it does cover all of these heights in between and then all the way down to 0 because it does land on the ground. So even though it starts at 15, we're not looking at where it starts left to right. We're actually looking just at the lowest and the highest point. So it's going to be all numbers between 0 and 35. So we can say the range is all numbers from 0 to 35. Now find h of x equals 0. That means find the input for when our output is 0. That was this point right here. I estimated that to be around 4.7. So I can say h of approximately 4.7 equals 0. That value represents when the height is 0. So it represents when the rocket is on the ground. And 4.7 would be, I believe, seconds. Yeah, time in seconds is what it says under there. So this represents the time that the rocket hits the ground. And we can say about 4.7 seconds just to give a value for it, even though they didn't really ask for that in the sentence. And that's it for question 5. So let's look at question 6. This is looking at cafeteria meal plans. So Mai has to decide between 2 cafeteria meal plans. Under Plan A, each meal costs $2.50, and under Plan B, 1 month of meal costs $30. So it kind of sounds like we don't have a limit for a month of meals. So we're going to write an equation for function A, which gives the cost in dollars of buying n number of meals under Plan A. So if they gave us a cost per meal, that implies that we're going to multiply. So I would say A, as my function name, of n number of meals is equal to $2.50 multiplied by every number of meals. That would be my equation here. Now you don't need to include the 0 on it, so you could say 2.5n, but when we're talking about money, I like to include all of the cents. Okay, now for part B, it says write an equation for function B, which gives the cost in dollars of buying n number of meals under Plan B. So B of n, and they just said this costs $30. That means it doesn't matter how many meals I buy, so I don't actually have to put an n on this. I can just say B of n is equal to 30. So Mai estimates she's going to buy 15 meals per month. Which meal plan should she choose? And explain your reasoning. So we want to make sure that if Mai's only going to buy 15 meals, we want to make sure that we're choosing the cheaper plan. So we're going to actually plug in and say A of 15, and then we're going to compare that to B of 15. So this would be 250 times 15, and that amount, A of 15, if we multiply that out in a calculator, this is going to be 3750 or 37.5. And I know that B of any number of meals, even if it's 15, is still 30. So I would say that plan B costs less for that amount of meals. So I'm going to say plan B, because it will cost her less money. Oop. It will cost her less money. Okay. And I think that did only have A, B, and C, so I paused for a second there to double check. And I do have more problems on my version of the homework, but this is where the homework assignment for my class ends. So thank you for joining me for this assignment. This was the Unit 4, Lesson 11 cumulative practice problems for Illustrative Math, Algebra 1.